Alright guys, so today we're going to be working on 13.1, just reviewing back through exponential growth and decay. What's happening is every week you guys are going to have 2 videos to watch and 2 homework assignments to do. Those assignments will be due at 11:59 p.m. every Sunday night, so make sure that you guys are keeping track of that. All assignments, everything due at 11:59. That includes a weekly assessment, just a quick overview of what we've covered that week, whether it just be a review, a couple of review questions, whatever that may be. That will also be due Sunday night at 11:59. And if we have a test this week, or whatever week we are working on, that will also be due at that time. New assignments will be posted by 9 a.m. the following Monday. That way you guys can work through that next batch of assignments. And all assignments will be posted on Schoology. So make sure that you guys are keeping track of that. If you guys have any questions as you're working through these problems or anything like that, just send me a picture of what problem you're having trouble with in an email and let me know what question you have on that problem. That way I can go ahead and work on that and make sure that you guys have access to that. Pause these videos as much as you guys need to whenever you're going through them. If you're having trouble understanding them, play through them again. Contact me, whatever you need to do. Use them to help you while you practice. The methods aren't going to change with these, so just keep track of that. These are the notes that we covered before we left, but that was about 3 weeks ago, so I want to make sure that we cover this once again. So, today we're covering 13.1 exponential growth and decay. What you guys will be tested on is I can identify exponential growth and decay, write exponential growth and decay functions, and solve exponential growth and decay applications. So those are the 3 things that we'll be going through today. So, just a quick overview. Exponential functions are always written in the form f of x or y, this is the same thing as y if we recall, is equal to a times b raised to the power of x. The thing that makes exponential functions exponential is that the value that we're plugging into our independent variable is our exponent, x. So, a breakdown of what these variables represent when we're working on these. First off, x is equal to time. So oftentimes we're going to plug in the number of years, the number of time intervals in for x. It's our independent variable, so that's what we plug numbers into. Our a value, the number that comes first, the number that is not raised to the power of x, that is our initial amount, otherwise known as our y-intercept. So whenever I'm going to find my y-intercept, whenever they ask me of that, I'm going to have a point 0, a, where a is. That's how I can easily find my y-intercept here. And if they give us a word problem, it's the initial amount, the amount that we started with. That's going to be our a value whenever we set up an equation. That initial amount is a. B is equal to our growth or decay factor. So b is a very specific variable that's unique to exponential functions. B is always the variable that's raised to a power of x. Now, I know that we're going to have growth if our b value is bigger than 1. If b is bigger than 1, it's growth. If b is less than 1, it's decay. So if b is smaller than 1, decay. B is larger than 1, growth. Now, to put into perspective what b is, well, b is equal to 1 plus r. Well, what this means is that we're starting at 100% always, because anything times 1 will not change the value. Then, from there, we're either adding, as we see in growth, or subtracting, as we see in decay, our r value from that. And that r value is how much we're growing or decaying by, the percent that we're increasing or decreasing by. That's what r stands for. So that's where this 1 plus r, 1 minus r comes in. So I can also replace that b value with 1 plus r if it's growth, as we can see in this function here. F of x is equal to a times 1 plus r raised to the power of x. Or if it's decay, I can substitute 1 minus r for b. So y is equal to a times 1 minus r, that's replacing b, raised to the power of x. Now, that r variable as well, that may add more confusion to this in itself. R is just the growth or decay percent rate of change. So again, it's how much we're growing by in a percent, or it's how much we're decaying, how much we're decreasing by, written as a percent. Sorry. So This is an important note for you guys right at the bottom here. This note says to change a percent to a decimal, divide the percent by 100, or move the two decimal places to the left. Example, if I have 5%, well, my decimal place would typically go right after the 5. If it's 5%, I'd move it 2 places to the left, giving me 0.05, as we see right here. Now, if I need to switch it from a decimal to a percent, then I'd move that decimal place 2 places left, and that'd give me back at 5%. So depending on whether we're moving left or right, depends on whether we're going from a percent to a decimal or a decimal to a percent. So, it says, now, think about what happens when you take Tylenol. Why doesn't it work forever? Well, the way that Tylenol works is that our body slowly filters out the Tylenol in it. So we're slowly losing that effect that we have from Tylenol over time. Now, that's a decay. So the Tylenol is decaying within our body. The amount that we have in our body is being decayed. And that happens over time. And that's why it doesn't work forever, is because our body is slowly filtering through it. So it's already at an exponential decay type problem where we're losing the effects slowly over time. And that's why it doesn't last forever, but it doesn't necessarily leave our body either. It gets very, 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 very small eventually, where it doesn't really even matter. But if it is exponential, then it doesn't actually ever completely filter out, though we know Tylenol will eventually get out of our body because we will filter it out through our regular channels. All right, so exponential growth versus decay. State whether the formula models growth or exponential decay. Justify your response. So your justification doesn't need to be super long or anything like that. And if I want to know whether it's growth or decay, I look at our B value. So if my B value is smaller than 1, decay. If my B value is larger than 1, growth. So starting this off, y is equal to A times B raised to the power of x. So the first thing that we need to do is identify B. Well, in this case, in letter A, B is 2/5. So B is equal to 2/5. Is 2/5 larger than 1 or less than 1? Well, 2/5 is less than 1, so this is a decay problem. So as you can see, I wrote decay, and then I had my justification. 2/5 is less than 1. All right, number 2. Again, we look for our B value to get started. In this case, it's 5/3. It's whatever number is being raised to the exponent. So B is equal to 5/3. Now I know 5/3, if I change that to a mixed number, B is equal to 5/3, that will give me 1 and 2/3. Now I know 1 and 2/3 is greater than 1, so this would be a growth function. Again, I have my explanation, my justification, and I also stated whether it's growth or decay. So go ahead and try these 3 on your own. Pause the video for a sec. Try these 3 on your own, and then I'll be going through them in just a minute. All right, letter C. First off, we find our B value as 3. Now, 3 is greater than 1, which means that this is a growth function. So letter C is growth because B is greater than 1. 3 is greater than 1. Letter D. Our B value in this case is 1/3. Well, 1/3 is about 0.33. It repeats forever. And I know that 0.33 is less than 1, so letter D is decay. And lastly, letter E. Our B value is 2/3. Well, 2/3 is about 0.67. It repeats forever as well. I know that 0.67 is less than 1, so this would also be a decay function. So those are our 3 answers for letter C, D, and E. Make sure that you understand this concept before you move on. If you have questions on this, please make sure that you email me, and that way I can help you out with this. All right. Example 2. Calculating the growth or decay percent rate of change. Now, this is the most tricky part. This is our R value that we're trying to find here. Now, states if R is greater than 1, so if the factor, that's B, if B is greater than 1, we automatically know that we have growth. And if we have growth, we can use the formula B is equal to B is equal to 1 plus R. So that's how we can find R. So if I do some simple algebra with this, I can calculate for R. Now, if B is less than 1, if B is smaller than 1, we know it's decay. So we can use the function B is equal to 1 minus R. So depending on whether we have growth or decay, we're going to use one of these two formulas. And the only thing that changes is growth we have plus, decay we have minus. Now, a big tip here. If you get a negative number, use the other equation. You should never get a negative number when you're dealing with these R values or these B values. If you do, switch the equation that you're using. So for instance, if I get a negative number here, I say that B is equal to -4 and I get R is equal to -5 as a result. I switch whatever problem I'm doing. I go ahead and I'd go down to this other one. So again, if you get a negative number, just switch equations. That's the big hint here. Now, again, we talked about this briefly earlier. What does the 1 represent? Well, 1 represents our whole, where we're starting from. If I multiply by 1, it's not growing or decaying, it's just staying the constant rate. So the 1 represents the constant when we're at the starting point. If I don't multiply by 1, then it's going to change it drastically. For instance, if I multiply by 0.5 and I forget the 1 in front of it, then it's going to change my answer drastically. So don't forget this 1 here. Extremely important that you guys have 1 inside both of these formulas. If not, it'll throw it all off. All right, let's go ahead and try out some example 2 problems. So, number 1, if B is equal to 1.02, calculate the growth or decay rate. Well, first off, is this going to be growth or decay? Well, B is equal to 1.02, and I know that 1.02 is greater than 1, so this would be a growth function. If it's growth, then we can use the formula B is equal to 1 plus R, and I know that B is 1.02, so I'll go ahead and plug that in for B, is equal to 1 plus R. From here, I just solve for R by subtracting 1 from both sides, and we're left with 0.02 is equal to R. Now, don't forget, this is a percentage, so I need to switch this 0.02 to a percent. I take my decimal place, and I move it 2 places to the right, giving us 2% is equal to R. That's our answer. For number 2, this time B is equal to 0.92. I know 0.92 is less than 1, so we have decay here. So we're looking for a decay rate. So go ahead and plug that into our formula. B is equal to 1 minus R, because once again we're using minus because it's decay. And we'll have 0.92 equals 1 minus R. If I subtract 1 from both sides, we're left with negative 0.08 is equal to negative R. Now, I know that we see a negative here yet, but R is not by itself. So from here, I divide both sides by -1 to get R by itself. We're left with R is equal to 0.08. From here, I move my decimal place 2 places to the right because, again, this is a percentage. This should be written as a percent. And we're left with R is equal to 8%. So this is an 8% decay for number 2. And for number 1, this was a 2% growth. So that's how you can find out how much your savings are growing or decreasing by. It helps in reading the stock markets. With recent events, it helps calculating what's happening, the percent rate that viruses can spread, things like that. So this is really useful information, and it helps people either make a lot of money or think about things in a different perspective, and helps with scientific studies as well. So go ahead and try these 3 out on your own, numbers 3, 4, and 5, and then I'll be posting them in a second. If you need to pause the video, please do. All right, so number 3. Looking at this, we have a growth function because b is equal to 1.97, so I know it's growth. So therefore, I can use 1.97 is equal to 1 plus r. Because again, we have growth, so I'm going to use the plus. I'm substituting 1.97 in for b. Sorry. So 1.97 is equal to 1 plus r. I go ahead and I solve for r. We get 0.97 is equal to r. Switch that to a percentage, and we get 97% is equal to r. Again, this is growth, because b is larger than 1. Number 4, our b value is 3. Now, that means that I know that this is growth right away, because b is greater than 1. So we have 3 is equal to 1 plus r. Subtract 1 from both sides, and we get r is equal to 2. And then I have that decimal place at the end there. If I need to switch this to a percentage still, this is just written as a decimal. I move my decimal place 2 places right. I can fill those in with zeros as placeholders. And we have r is equal to 200%. Again, this is also growth. Our final one, 0.15, is our b value. So this is decay. So we have 0.15 is equal to 1 minus r. Again, we're using minus because it's now decay. At this point, I subtract 1 from both sides, add in my zeros on the left side to make it a little bit easier. We get r is equal to negative 0.85. Now, I'm sorry, this should be a negative r there. From here, we divide both sides by negative 1 to get rid of our negatives. And again, it's negative because it was negative right here. And when I divide by those negatives, the negatives disappear, and this leaves us with r is equal to 0.85. Now I switch this to a percentage by moving my decimal place 2 places to the right. Left with r is equal to 85% decay. So that's a massive decay. All right, only a couple problems left. Some application problems. So for number 3, a rare coin appreciates at a rate of 5.2% per year. The initial value of the coin is $500. Is this growth or decay? So first off, the word appreciates. That means that's growing in value after each day. So this would definitely be a growth function. Looking at what they give us, write an exponential function that models the value of the coin after t years. So in this case, if it's t years, x is going to be t years. Our a value is our initial value, which they tell us is $500. So a is 500. Our r value is the rate of change, the percentage, 5.2%. I need to switch this to a decimal to plug it into our equation, so I move my decimal place 2 places left this time because I'm going from percentage to decimal, which gives us 0.052. So r is equal to 0.052. We know that this is growth, so our b value should be 1 plus r, which means it's 1 plus 0.052, which is 1.052. From here, I can go ahead and plug this into our formula. Y is equal to a, which is 500, times b, 1.052, raised to the power of t. Next, we want to know how much the coin will be worth in 20 years. So I just plug 20 in for x. So 20 years gets plugged in for x, and in this case, it's the variable t. So we have y is equal to 500 times 1.052 raised to the 20th power. If I plug this into a calculator, we get y is equal to $1,378.11. And that is our answer. All right, moving on to our next example. Example 3. As technology advances, the price of many technological devices goes down in price. One brand of flat-screen television sells for $1,500. The price is expected to decrease by 6% per year. Is this growth or decay? Well, looking at this is definitely decay. It's decreasing in value each year, so that'll be a decay function. So we know that we're losing value here. So would I use b is equal to 1 plus r or b is equal to 1 minus r? Well, the answer here, it's decay. So we're going to go ahead and use b is equal to 1 minus r. Now, we want to write our exponential function. We know our a value is our starting cost, $1,500. Our b value, a is, my bad. A is equal to $1,500. Our b value is equal to 1 minus r. Well, r is 6%. I move my decimal place 2 places left, which gives me 0.06. Again, this is decay. So b is equal to 1 minus 0.06. b is equal to 0.94. So from here, I can go ahead and write my equation. Y is equal to A, 1,500, times B, 0.94, raised to the power of t, because we're working in t years. From there, find the price of the TV after 5 years. Once again, we just plug in 5 for t, and we get Y is equal to 1,500 times 0.94 raised to the 5th power. If we plug this into a calculator, we get our final answer as $1,100.86. So after 5 years, that TV's lost almost $400 in value. All right, try this last one on your own. Pause the video if you need to. I'll be going through it in just 1 second. All right, so a 3-bedroom house in Burpville was purchased in 1999 for $190,000. Housing prices are expected to increase 1.8% annually in that town. Is this exponential growth or decay? Well, this would be a growth function because we're growing in value, we're increasing in value. And so I can go ahead and write this out. I know that we're starting off at $190,000. So my A value is 190,000. My B value is equal to 1 plus our R value. Well, in this case, R is 1.8%. I move that decimal place 2 places left, giving me 0.018 is what is equal to R. From there, I can write out my function. Y is equal to A, which is 190,000, times B, 1.018, raised to the power of t. Next, we want to find the price of the house in 2004. Well, to do that, we need to know how much time has passed between 1999 and 2004. So 2004 minus 1999 will give us 5 years. So in 5 years, we're going to go ahead and solve. So we plug 5 in for our t variable here, and that will allow us to solve for the price of the house in that amount of time. So y is equal to 190,000 times 1.018 raised to the 5th power. That will give us our final answer as $207,726.78. So in 5 years, it's increased that amount. In what year will the house be more than $300,000? For this type of problem, I highly encourage you guys to use the table function in the calculator or guess and check. So if I know in 5 years it's around 207,000, I can jump up to about 20 years and see where it's at there. If it's still not at 300,000, then I can jump up to 25 years, check there, and then go up year by year. In fact, if we use the table function, you find out in year 26,
year 26, we're actually at $302,131. So to find out how many years that is, I'd go ahead and take 1999, our starting year, add 26 years to it, and that'd leave us with 2025. All right. Now, there are some homework problems for you guys on Schoology. Make sure that you guys get that extra practice in. If you guys have any questions for me, just make sure that you send me an email. Let me know what's going on. Other than that, thank you guys. Stay safe. I'll talk to you soon. Have a great rest of your day.